Welcome to the second part of our 2.8 notes. So, just a reminder from part one, we talked about the definition of the derivative. A reminder that all the derivative is the slope of your tangent line. So, because we knew slope of tangent line from the chapter 2 material, we know that f prime, or your derivative, is equal to this following limit formula here as h goes to 0, if this limit exists. So f prime is the slope of the tangent line at some point x if f prime exists. So I have this lovely curve here, and this is our graph of f, and our job is to graph what f prime might look like. So I like to start with, where does it look like I would have tangent lines with a slope of 0? So if I take a look at where x is -5 and where x is +5, our maximum and minimum, if I were to draw a slope or a tangent line and take a look at the slope, I would see that I have a slope of 0. And we saw this yesterday with example number 2. So what that means is, if I'm trying to draw f prime, if I think about it as a table of values, I've got x values and I have f prime values, or y, right? So when x is -5, I have an f prime value of 0. And when x is +5, I also had an f prime value of 0. So I'm going to put these points on my graph. Okay. Now I also can notice that if I draw tangent lines anywhere to the left of -5, any of these tangent lines here would have positive slopes. Also, if I'm to the right of +5, anywhere I draw a tangent line would have positive slopes. So this means if x is less than -5, we have a positive y value, or if x is bigger than 5, we have a positive y value. We don't know what those y values are, but they're positive. So that means everywhere to the left of 5 over here, we have positive y values. So somewhere up here is where my graph would go. Okay. Again, unless I can calculate all these slopes, I don't know exactly where those are, but I know this has to go up this direction somewhere and up this direction somewhere. That's the best I know right now, without actually starting to calculate what these slopes are. Okay. I also know that if I were in between -5 and 5, anywhere I draw slopes, these would all have a slope that is negative. Okay. And this one in the middle actually looks like it's pretty close to being -1 or -2. It doesn't get very steep. The red ones, as I continue forever to the right and to the left, those would get very, very steep, which is why I can say on my f prime graph that these would go on forever. But in the green portion in the middle, it only gets so steep before it goes back to 0. So it seems like this is the steepest it is in the middle. And it looks like our slope is approximately, it looks like it might be about 2 if I drew that a little bit nicer, or -2, sorry. So that means that when I'm drawing my f prime, my slopes are negative. They need to be down here somewhere, but it looks like the smallest it gets is -2. So from -5 to 5, my slopes are negative. Oops. Can't fit all that in there. Let's make my table a bit bigger and make this a little nicer. Okay, my slopes are negative, so they need to be down below the x-axis. And it looks like the smallest one is about -2. So, and it's in the middle of the two of those blue points there. So I'm going to draw it like this. Okay. Again, you might say that, oh, well, to me, it looks like -1, or to me, it looks like -3. Then that's fine. You can put that there. But I know that it doesn't go down to like -20, for example, because that's not a very steep slope, that green slope that I drew. Okay. So this would be the graph of f prime. Okay. Now we're going to talk today about something called differentiability. So we said last day that a function is differentiable if this limit exists. Okay. So just a couple sort of notation issues here. To differentiate, if I ask you to differentiate something, I'm asking you to find the derivative or take the derivative. We say a function is differentiable if the derivative exists on a certain interval, then the derivative would need to exist for every number in that interval. The derivative can only exist if the slope of the tangent exists, because the derivative is the slope of the tangent. And if f is differentiable, then it must be continuous. However, if it's continuous, it does not necessarily mean it is differentiable. Okay. So the reason it has to be continuous, if we know it's differentiable, it must be continuous, because if it's differentiable, we were able to find the limit. And in order to find the limit from both sides and for it to be equal, then we would need to be continuous here. So we have a couple ways that we are not differentiable. So from chapter 2, okay, we have, if we have a jump, this would not be differentiable at this value, x is a, because the limit from the left and the right are not equal. And therefore, we can't draw a tangent line here where we can approach from both directions. Okay. If we are removable, okay, we are not differentiable. Same thing, we cannot draw a tangent line at that point because there is no point. There's a hole. Okay. And then infinite, this could be infinite to negative infinity, positive infinity, or different directions could be approaching different infinities. And again, we cannot draw a tangent line. It would be a vertical tangent line where our slope would be does not exist. A vertical line does not have a slope that we can find. Okay. The other two that are new are a corner. And that's because technically at this point, you're drawing a tangent line both directions. Okay. So this is an example of one that is continuous, but is not differentiable. So I like to think of this as, if it's differentiable, it's continuous. So kind of like all thumbs are fingers, but just because it's continuous does not make it differentiable. So just because it's a finger does not mean it's a thumb. Okay, so kind of like the all thumbs are fingers, but not all fingers are thumbs bit. Okay, so the last one is there's two different ways that this will look, and it's a vertical tangent line. Again, if you have a vertical tangent line that you can actually draw, the infinite one, we can't draw a vertical tangent line because we have an asymptote there. These two, we can actually draw a vertical tangent line. But again, that would mean that we cannot find a slope, which means we cannot find a derivative. So this would be something like this, or something like this. Sometimes this second version of vertical tangent line is a little bit difficult to tell the difference between this and a corner. So there's a little bit of leniency between labeling those two there. Okay, so let's try some. So for example, if I take a look at these two graphs, the question is, can we tell what types of continuity we have will help, or just where are we not differentiable. So, for example, right here at -1, we have a jump. Here at 0, okay, I would say that this would be infinite because you've got that left side going to infinity. If you said jump, I would probably be okay with that. Here at 1, we have removable. And over here at 2, we have a corner. If you want, you could pause the video here and try B on your own. If you would like to see the answers just right away and write them down as examples, we'll keep going. So we have discontinuity at x equals -2. This would be infinite. We have discontinuity at x equals -1. This is a vertical tangent line. We have discontinuity at 0, also a vertical tangent line. And we have discontinuity at 2. This is removable. Okay. We have another example here where we are going to be given f and sketch f prime. If you want, again, we did one of these on the front page. So if you would like to try this on your own, you could again pause the video here and give it a try. But otherwise, you can continue. So first we see that we have two parts here where it looks like we have corners. So here and here at x equals ±5, we have corners. So that means f prime does not exist. Not possible to differentiate it those two. So what we need to figure out is, well, if we drew tangent lines, what would the slopes be at all these other points? So if we take a look at this line, everywhere I draw a tangent line, it's actually going to be the same slope as this actual line here. Okay. And if I look at that, the slope of that line here is equal to 1. And the slope of the one on the right is equal to -1. So again, if I want, I can draw myself a little table of values if this helps. So we have when x is less than -5, x at -5, we see we're going to have a little span between -5 and 5. We have when x is exactly 5 and when x is bigger than 5. So as we've seen here, if x is -5, we have does not exist. X is 5, we have does not exist. If x is less than -5, we had a slope of 1. And if x was bigger than 5, we had a slope of -1. So if I have a slope of 1 everywhere, that means my y is 1 everywhere to the left of -5. So starting at -5 all the way to the left, we would have a y value of 1. But because we do not exist at -5, we are going to have an open circle indicating that we do not have a point here. Okay. Then when x is bigger than 5, we had a value of -1. So if I go down to a y value of -1 at 5, again, we're going to have an open circle because we have that this f prime does not exist when x is 5. Okay. So the one that we're missing is in between -5 and 5. And again, if I draw tangent lines all along here, my slope for every tangent line would be 0. So that means between -5 and 5, we have y values of 0 if we're graphing f prime. And again, at -5, we do not exist. At 5, we do not exist. And we can connect those because all of the values in between are 0. So it looks like this weird little step graph here with open circles where we change from piece to piece. Okay. The last little bit for today is just a couple special limits. You would not be expected to memorize these, and we might not make it there this year due to going a little bit slower with this online learning business, but you will eventually, if you take calculus in university, or if we get to it this year, you will learn something called L'Hopital's rule. And that would prove why these all work. For now, you can take my word for it. We can't do L'Hopital's rule yet. You don't know the math to be able to solve it, but we will learn the math you need this year. But for now, these special limits, it might be helpful to write them down somewhere on almost like a little cheat sheet, formula sheet type thing to reference when you need. And so these are just a couple special limits, and it will help you evaluate some that you might end up when you're doing h approaches 0. You could end up with some that kind of look like this. So if I want to evaluate this limit, the first thing I would choose to do always is rewrite tan in terms of sine. So I would rewrite this probably as sine x over cosine x over x. And this doesn't look great. So I would choose again to rewrite this. Oops, not x approaches x. That should be x approaches 0 as sine x over cosine x times 1 over x. If I do that, I can see that this kind of looks like if I had this sine and this x, this would look like this one. But a reminder from our limit laws, I'm allowed to rearrange this. So I would choose to rewrite this once again as sine x over x times cosine x. And a reminder from our limit laws, what we're allowed to do here is break this down into the limit of sine x over x times the limit of 1 over cosine x. And now I can evaluate this. I have my special limit here. This is equal to 1. And the limit as x approaches 0 of 1 over cosine is 1 over cosine 0. And remember, cosine of 0 is equal to 1. So this is 1 times 1, which is equal to 1. Okay. So again, a reminder, there are way more questions here than you need. If you want, you can just do the 5th edition or just the 7th, or just again, pick out a couple questions. If you're like, oh, the graphing ones are hard and you want to try those, try those. Pick out some to try, do more if you need. Don't do too many, don't overwhelm yourself. Pick some to try or do the board questions, and that should be good.